Hello everyone, welcome back to the channel. This is part 3 of a video series where I'm attempting to explain every Sudoku solve technique. Make sure to check out part 1 where I explain the basic techniques and part 2 where I explain advanced group techniques. Anyway, at the end of the last part, we discussed almost hidden sets. And this is a category of techniques where you can look at the overlap between groups of candidates in similar positions to essentially lock them into place and cause certain eliminations. And almost hidden sets, in my opinion, are really cool from a logic perspective. But to be honest, they don't come up very often. And when they do, they're pretty tricky to spot. So in this part, we're going to cover a different category of techniques that focuses only on a single digit at a time instead of focusing on groups of multiple different digits. Because of this, these techniques are much easier to spot and much more common. And for some reason or another, this category of techniques is called a fish. So let's go fishing. So the basic idea of fish is we're looking at different ways to group candidates of a single digit into rows, columns, and boxes. And if we're able to find one way to group those digits that covers all of the same instances as another way to group those digits, we could eliminate any excess candidates from those cover sets. So let's go into a little bit more detail of what we mean by this. So here we have a grid from Sudoku, and the digit we're going to focus on in this grid is 5. So let's go and draw our attention to rows 2 and 5 right here. I want to go and highlight those in yellow. Those are going to be called our base sets. Now, our 5s are contained in these 4 cells of those base sets. Those are going to be called our base candidates. And just by the rules of Sudoku, we know that a 5 has to appear exactly once in each of these rows or base sets. So the trick with fish is finding another way to cover those base candidates using the same number of sets. So in this case, it would be 2 sets. So you'll notice if we look at columns 5 and column 8 here, I'm going to go and highlight those in blue. Those cover our base candidates, and so those are going to be called our cover sets. And since we know that 5 must appear exactly once in each of our base sets, that means the 5 has to appear in those exact same positions in our cover sets. So anywhere in our cover sets a 5 exists that's not one of these base candidates, we can go ahead and eliminate those. So the only place that occurs is this 5 right here. We can go ahead and eliminate that as a candidate. And that leaves us with a naked single, which would be an 8. Now, if that logic doesn't make a ton of sense to you right now, don't worry. The simplest occurrences of fish can be explained a lot more intuitively. But as we get to more progressively complex techniques, this base set cover set logic will become more necessary and hopefully a lot more clear. But without further ado, let's get into one of those simpler occurrences of fish. X-wings are the simplest occurrence of fish, where we have 2 pairs of bilocal candidates and their locations overlap. The grid we just went over was an example of an X-wing, and this grid from Sudoku is also an example of an X-wing. And just kind of as a spoiler alert for the rest of the video, we're going to be using Sudoku a lot because, in my opinion, they have the most comprehensive resources on fish. But anyway, let's go ahead and look into this grid in a little bit more detail. We're going to be looking at the 1s in particular. And let's look at columns 1 and column 5 here. So you'll notice our candidate of 1 can only appear in 2 locations in both of those columns. And you'll notice both of those locations share the same row. That's what I mean when I say they're overlapping in the locations. So for example, this really only leaves us with 2 possible states. For example, if we were to have a 1 here, then we couldn't have a 1 here, therefore we'd have to have a 1 here. That's one possibility. And if we didn't have a 1 here, we would have to have a 1 here, and that would only leave us with a 1 here in this row. So that kind of creates an X pattern with each of these possible diagonals here, and that's why it's called an X-wing. But you'll notice in both of these combinations, we can't have any other 1s in these rows. Those being rows 2 and rows 5. So we can go ahead and eliminate any other 1s in those rows. Now we could kind of look at this from a base set cover set logic as well. If we were to define our columns 1 and columns 5 as our base sets, we could contain all of these 4 base candidates within rows 2 and rows 5. And that allows us to eliminate any cover candidates that aren't also base candidates. So that is the X-wing. Now, swordfish are a lot like X-wings, but instead of having two lines where you're sharing two locations, you have three lines where the candidates are sharing three locations. So this is another grid from Sudoku, and let's go ahead and focus on the candidate of 4 here. So if you take a look at rows 2, rows 4, and 7, you'll notice that the 4s are limited to 3 possible columns, those being columns 2, 3, and 5. And this means that since we have 3 rows which share the same, 3 columns, those rows can essentially claim those columns, and all the other 4s um, can be eliminated. There's quite a bit of them, so it's taken me a while to highlight all of them. Oh, and there's this one as well. But yeah, so we could look at this from a base set cover set logic as well. We have our 3 rows. These are our base sets. And those rows can be, the candidates in those rows can be entirely covered by our 3 cover sets, which again are columns 2, 3, and 5. And now that allows us to eliminate everything else outside of those cover sets. Now, the cool thing about swordfish is that the candidates don't have to be in all 3 of those locations. For example, let's say if we didn't have a 4 as a candidate here, we didn't have a 4 as a candidate here, and we didn't have a 4 as a candidate here, you'll notice that still the candidates across these 3 rows are still within the same 3 columns, even though the exact combination of those columns is different for each row. Our rules still apply, and we could still make those eliminations because at the end of the day, these 4s are fighting for the exact same 3 spots on the column, which means nothing else can occupy those spots on the column. So that is a swordfish. Jellyfish basically extend the same principle of X-wings and swordfish, but to a size of 4. So we have 4 rows where a certain candidate overlaps in the same 4 columns, or vice versa. And we have another grid from Sudoku here to demonstrate that. And the candidate we want to focus on in this grid is 7s. So that's all the 7s highlighted. And unless if you're some kind of Sudoku prodigy, it really isn't clear as to where the jellyfish is just by looking at it. So if you look at our base sets and cover sets, which we already have highlighted, you can see where the overlaps are and where we could eliminate. So any of these 7s that are in the blue but not in the yellow, we could eliminate all of those essentially. But again, that isn't clearly obvious just because larger fish are generally harder to spot. When it comes to actually finding fish in a Sudoku grid, my strategy is to just pick a certain candidate and go row by row or column by column and see if that row can qualify as a base set for a fish of that size. So let's say I'm looking for jellyfish, and again focusing on 7s, and we already know there is a jellyfish here, as we just explained. But let's say we didn't have any of the highlighting and we didn't know that right off the bat. Looking at this first row, we see there are 6 candidates. So a jellyfish is 4 rows of 4 candidates, so that doesn't really work. So we know this first row can't participate in the jellyfish. Same thing with this second row here, 6 candidates, too big to be a jellyfish. And then we get into this third row, we have 4 candidates, right? And that's the maximum number of candidates we can have in a normal jellyfish. So if this could be a row, a base set in the jellyfish. So let's assume that it is. This next row, we also have candidates in those same 4 positions. So we're not adding in any extra positions, which means still could continue to be a valid jellyfish. We just need to find 2 more rows in order to make that work. Looking at this fifth row here, that has 7 candidates. So that is definitely too big to be a jellyfish. This next row, 4 candidates in the same 4 positions as our previous 2 rows. So we just need to find 1 more row in order to make this a proper jellyfish. And we could do that in this very next row. We only have 3 candidates, but it works because those 3 candidates fall within those same 4 positions. So that's kind of my strategy for looking for jellyfish. It takes a while if we really want to be thorough and make sure there's no fish for any candidate in the grid. But the nice thing about jellyfish is that although technically you could apply the same principle and look for a fish of a size 5, 6, or 7, it really isn't necessary because every fish can be found with a complementary fish. So, what I mean by that is if we have a size 5 fish, then since there's 9 spots in the grid, there will be a complementary size 4 fish that we could find where we could make that same deduction. That essentially means that we don't really have to look for size 5, 6, or 7 fish just because they're so much harder to spot. There will always be a fish of size 4, 3, or 2 that we could look for instead. But yeah, that is the jellyfish. Fins are basically imperfections in the structure of a fish, and they happen when we have an extra candidate in the same box as our base candidate. So here we have another grid from Sudoku, and our fish candidate for this one is going to be a 7. So let's go through column by column and take a look at those 7s. So first column, we got our 7 in 2 locations here. Let's go and jump over to the fifth column. We also have our 7 as bilocal in 2 locations, and one of those locations overlaps. So we're looking at 3 total rows. And then let's go and jump over to this final column here. If our 7 was only in this row 5 and row 3, that would make it a swordfish, right? Because we'd have 3 columns with candidates sharing those same 3 rows. And then we could do the same eliminations where we eliminate any 7s that are in the cover sets but not in the base sets. But we have this extra candidate up here in this cell, and that is going to be our fin. And that prevents us from having a perfect fish. So you may be wondering, okay, that's unfortunate, but what's the point of talking about this? If it's not a fish, then we can't do eliminations. And that would be true for most of these cover cells. But if you take a look at this cell right here, you'll notice if we were to place a 7 here, then we wouldn't just be taking out this base candidate, we'd also be taking out the fin as well. And what we would be doing is forcing these 3 candidates in each of our base sets to compete for these 2 rows, which would violate the rules of Sudoku. Therefore, we can't have a 7 in this box, and we could actually go ahead and eliminate that 7. So essentially, the trick with fins is that any candidate that takes out a fin, any cover candidate that takes out a fin can be eliminated. And this is the case even if we had 2 fins in the same box. For example, if there's a 7 here as well, and we had these 2 cells were both fins, this elimination would still be valid. Again, as long as the fins are in the same box. But yeah, that is finned fish. Sashimi fish are just like fin fish, but you don't actually have your base candidate in the same box as your fin. So take this sashimi swordfish that we just went over, and again, 7 was our fish candidate. If we didn't have a 7 in this cell, then this would be a sashimi swordfish. And functionally, this is the exact same as just a regular fin swordfish. We can make the same elimination, which would be just eliminating the 7 in this cell. But sashimi fish are really interesting when it comes to X-wings in particular. So here's another grid from Sudoku, and our fish candidate here is going to be a 3. So let's look at columns 3 and column 6 here. So you'll notice that clearly row 3 is one of our cover sets, right? Because we have 2 bilocal columns and they overlap in row 3. But I have a question for you. Which of these rows is a fin on the bottom? Clearly, one of them is because the 2 cells don't share the same row. But you could make the claim equally valid that each one is a fin. For example, you could say, okay, well, row 7 is the cover set here, and this cell right here is a fin, and this is just a sashimi X-wing. And then you could argue from there that you can make the elimination of a 3 here. But you could also make an equally valid argument that row 8 is actually the cover set, and therefore you can make an elimination of a 3 in this cell. And both of those would be valid eliminations. So the cool thing about Sashimi X-Wings is that both of the cells can qualify as fins, and you can make 2 eliminations instead of just 1. So up until this point, we've been looking at when our base sets and cover sets are lines. When we have n rows of candidates that are fighting for the same n columns, or n columns of candidates that are fighting for the same n rows. Franken Fish are what happen when you add boxes into the mix. So we have another grid from Sudoku here that kind of illustrates what a Franken Fish is, and 8 is going to be our fish candidate. So let's say we're looking at this grid, looking at the 8s, and let's say we're looking for a jellyfish in particular. So I'm going to start with this first row, and we only have 3 candidates, so small enough to be a jellyfish. Go into the second row, we have 4 candidates in the same positions, still could qualify as a jellyfish. Let's go down to this fifth row, 4 candidates in those same positions. Now, if we were to find one more row that has candidates that are only in those 4 positions, we would have, a regular old jellyfish. But we don't have that. What we do have, though, is if we look at our bottom left box, by the rules of Sudoku, we know an 8 must appear somewhere in this box. And if you notice, the only 3 positions which it can appear are already in those 4 columns, really only 2 of these columns that we've identified as cover sets. So what we could do is we could treat this box as one of the base sets instead of treating another row as a base set. And if we were to do that, this would be a Franken Fish. And we can make eliminations in all of these cover sets that have an 8 that are not within our base sets. So that is the Franken Fish. So a Frankenfish are what happen when you combine rows and boxes or columns and boxes. Mutant fish are what happen when you combine all 3. So here we have a grid from Sudoku, and as you could probably tell by the fact that it looks like a Picasso painting, mutant fish are really not intuitive or easy to spot. So in order to figure out what's going on, we really have to rely on our base set cover set logic. So for this grid, our fish candidate is an 8. And if we take a look at all the positions where an 8 is, we could identify our base sets. So our base sets are going to be row 1, row 6, column 4, and column 7. And this is going to contain all of our base candidates, which we could see here. And you'll notice that we can cover all of these candidates with 4 cover sets, those being column 1, box 3, box 5, and box 8. And then by our base set cover set logic, we could make eliminations in all of our cover sets that do not contain a base candidate. So that would be all of these cells. We could eliminate the 8 from all of those. Now, another cool thing about mutant fish is you could actually eliminate multiple fins at the same time that don't even have to be in the same box. So, for example, let's say we had this fish structure, but then we added 2 fins to it. So 2 base candidates that aren't covered by the cover set. Let's say we had one here, and let's say we had another fin here. So these 2 fins are in completely separate boxes, but there is still one cell that sees both of these fins, and that is this cell right here. And you'll notice it's in the cover set, but not in the base set, so it's already an elimination candidate for regular fish. If this candidate can see both fins, which in this case it can, then we could still eliminate this candidate. So again, if there are fins to your fish, it's not as powerful as a fish, but we could still sometimes cause eliminations if a certain elimination candidate sees all instances of the fins. But yeah, that is mutant fish. So in addition to extending the regular fin rules, mutant fish enable an entirely different type of fin called an endo fin as well. So here we have a grid here from GNXP, which is a Sudoku solving algorithm. And our candidate we're going to focus on here is twos. So um, as you notice, we have our base sets, which are rows 4 and then columns 2 and 7. And then all of the twos in there are covered entirely by our cover sets of box 4, box 6, and row 8 here. But you may notice something interesting with this cell in particular. We have a 2 here that is at the intersection of two base sets. Um, and that actually creates a big problem because the whole idea of fish is that we have n base sets, and each of those sets has a unique candidate. And that means if we're able to find another n cover sets to cover all those candidates, we know we'll have a base candidate to fill up every one of those cover sets. And that's what enables the eliminations. But if we have a candidate at the intersection of two base sets, that's a problem because that means that candidate could participate in two different sets at the same time, and then we would only have n minus one candidates for n cover sets, which essentially destroys the fish. For example, let's say if we were to place a 2 at this intersection right here, that would take care of both of our base sets, row 4 and column 7. And then we'll only have one base set, which will have one candidate for two different cover sets. And if you actually go through and solve this grid, we'd have a 2 there and then a 2 here in our last cover set. And you'll notice that that 2 is a candidate in our cover set that's outside of our base set, which wouldn't be allowed in a regular fish. So we could basically say that when we have an endofin, our grid is under constrained because we have a candidate that can satisfy two base sets at the same time. However, we can still make eliminations in any cells that see our endofin because then we're eliminating that as a possible position where you could satisfy two base sets at the same time. So in this grid, the only cell that sees our endofin and is in a cover set is this 2 right here. So we can go ahead and eliminate that. So to summarize, endofins are just like regular fins in the sense that they are imperfections in the grid, and we can only eliminate in cells that see the fin. The only difference is that they are inside the structure of the existing fish. That's why we call them endofins, as opposed to outside the structure of the fish, like regular exofins. So cannibal fish are essentially the opposite of endofins. Instead of having one candidate participating in two base sets at the same time, we have one candidate participating in two cover sets at the same time. And the reason this is a problem is because we're essentially uh, taking out two cover sets with one candidate, meaning we have to fit n base candidates into n minus one cover sets, which is impossible. So whenever we see an instance of cannibalism with fish, we're over constraining the set, and we could eliminate any candidate that participates in both cover sets. Here we have a really simple grid, also from GNXP, and our candidate here is going to be 9. Um, and we could define our base sets as box 1, row 2, and our cover sets as box 3, row 3. And as you can see, our cover sets do entirely cover the 4 candidates in our base sets. But we have this one candidate, which is at the intersection of row 3 and box 3, and it can participate in two cover sets at the same time. But you'll notice if we were to place our candidate, our 9, here, then we would be eliminating two cover sets at the same time, which would overconstrain our set. And you'll actually notice this would eliminate every single base candidate on the grid all at once, which then essentially leaves two sets empty. So we can't be having that. Even if this cell was covered by one of our base sets, for example, this still would be invalid to have our base candidate here because participating in two cover sets at the same time means that you are over constraining your set. So we can go ahead and safely eliminate the 9 in this box because of the cannibalism rule. So you're probably thinking about at this point, mutant fish, those are already complex enough, but now I got to worry about endofins, exofins, cannibalism. That's way too much to keep track of, right? That's where N by N plus K fish come in. And basically, this technique throws the idea of tracking your fins out the window and just says, if you have a number of base sets, what's the minimum number of cover sets you need to cover every single one of those candidates? And in a normal fish, you would have n base sets and n cover sets. That's an n by n fish. But if you would have a fin, you would need to add extra cover sets in order to account for that fin. So that's the plus k part of your n by n plus k fish. So when you're doing an n by n plus k fish, you find out your number of base sets, your number of cover sets. K is going to be the difference between your base sets and cover sets. And that's your k number for the whole grid. And then what you do is you go to each cell and see how many base sets that cell belongs to and how many cover sets that cell belongs to. And the difference between those is your k number for the cell. And the trick is, if you find any cells where your k number for the cell is larger than your k number for the whole grid, you could eliminate the candidate from that cell. And the reason for this is because if you were to place that candidate in the cell, you would be removing more cover sets than you would allow for in the entirety of the grid. So, for example, let's say you have a grid where you have 3 base sets and 4 cover sets, but you have one cell that belongs to 1 base set but 3 cover sets. If you were to place the candidate in that cell, you would be essentially satisfying 3 different cover sets, making the total number of remaining cover sets 1, whereas you'd only be satisfying 1 base set, making the remaining number of base sets 2. And having less cover sets than base sets is impossible because then you can't fit all of your candidates in your cover set. So let's go through an example here. I have this absolutely massive fish here. And this is courtesy of the Sudoku subreddit wiki. And I have all the base sets highlighted in yellow and all the cover sets highlighted in blue. So our base sets here are rows 1, 4, 5, 8, columns 1 and 6, and box 7. So that's 7 base sets in total. And our cover sets are rows 2 and 9, columns 2, 3, 5, 8, and 9, and box 5 and 8. So that's 9 cover sets total. So our K number for this whole grid is going to be 2. Now, we could go cell by cell here and calculate the K number for each cell. For example, let's start with this cell. This specific one belongs to only a single base set, and it belongs to a single cover set. So our K number would be 0 for the cell, no contradiction there. And we could go through and do that for every single one of these cells, but that's going to take forever. So I'm just going to go ahead and skip to our elimination candidate, which is all the way down here. This candidate belongs to 0 base sets, but it belongs to cover sets, the cover set in column 9, the cover set in row 9, the cover set in column 5, and the cover set in box 8, which brings our K number to 3, which is larger than the K number of our grid, which is only 2. Therefore, we can go ahead and eliminate our candidate, which is 7. I probably should have mentioned that at the beginning, but we'll eliminate our candidate of 7 in this cell. And with that, we conclude our video on fish techniques in Sudoku. Thank you to all the sources for the grids in this video, especially Sudoku. There will be links to each of those grids in the description. And thank you so much for watching. Make sure to drop a like if you enjoyed. We will be continuing this series. The next video is going to be on single-digit chains. So subscribe if you want to stay tuned.